Welcome to this lecture on cryogenic hydrogen technology. We were talking about the cryogenic hydrogen production, and it is in continuation to that hydrogen production part, and we were talking about the different conventional processes like steam reforming, partial oxidation and autothermal reaction reforming. And in that context, we have also learned that this resultant product, that is CO and H2 combination, needs certain amount of processing to get the H2. Like both CO and H2, both are equally important for chemical industries, and this production of hydrogen and CO using this steam reforming or partial oxidation or autothermal reforming, they are quite common in nature, and they are out of this as we have learned that the steam reforming process is mostly very common, but this partial oxidation is equally important. We will try to see about its use in coal gasification. So, we will talk about this part in this lecture, and so let us look into this. This is the concept is still hydrogen production, and we will be talking about the synthesis gas processing. Particularly here comes the role of cryogenics, and we will see how this cryogenic condensation and methane scrubbing, depending on the concentration of COH2 and CH4 mixture, they are in use. And finally, before that we will try to have a look into the application of these processes, which can be in future it can be used for our coal handling. You remember that we have talked about the coal for generating the hydrogen. So, in these processes we have, this is of course the steam reforming, and then we have learned about that it is giving us something at this product is coming at 850 to 920, as I was telling that this finally this product here this after this water gap shift reaction, this will give you the CO plus H2, and from there finally this will be the H2 product, which will be basically the raw hydrogen here at this point. So, this in between you need some condensation process or that CH4 scrubbing process to generate this raw hydrogen, and from there we have to finally get this PSA system to purify this mixture to generate the pure hydrogen. So, we will be looking into this reaction part, and also we need to keep it in mind that they are coming out this reaction taking place around this 850 to 920 degree centigrade. Similarly, for the partial oxidation part, we have seen that this this reaction at this at the exit of the reaction zone is nearly about 1200 to 1400 degree centigrade, and in the autothermal reaction part we have nearly about 900 to 1100 degree centigrade temperature. So, here again you see that after CO2 and H2S removal, we have some condensation process that we have talked about. This condensation process will generate the raw hydrogen, and this raw hydrogen will finally be purified in the PSA, pressure swing adsorption cycle, to give us the pure hydrogen. So, how this what is there in it, and what is getting condensed in this process, we will try to learn in this lecture. But before that, as I told you that this is of course the autothermal reforming process, where we have seen that the outlet or the syngas is coming around 900 to 1100 degree centigrade. So, you can understand that these processes are generating CO plus H2 and they are coming at high temperature. So, this we will try to discuss about this part in connection to the use of our hydrogen generation from coal. But this coal is also used this is already we have talked in the first lecture when we were talking about the hydrogen production, and in that context we have told that there are certain advantage we have told that this is certain there are certain advantage that it is available in low cost and they are abundantly available, and of course, there are negative features like the having CO2 emissions and etc. But at the same time this coal is also used for generating the power. So, in many thermal power plant you will find that if we look at the salient features that we have the coal fired thermal unit and for generating the power, and you will find that the most modern plants are where this coal is directly being fired or the combustion is taking place. It is having the pulverized coal or powder coal, and they are generating either supercritical steam that is coming at supercritical pressure and temperature, and the overall efficiency is of the order of 36 to 40%. But on the other hand it generates the greenhouse gas like SOx, NOx and CO2 and mercury. So, these are definitely are concern for us as we are more and more concerned about our environment. The release of these gases from the thermal power plant we cannot accept it any longer, but there are so many thermal power plants in India and in abroad, and we have seen that there is a good amount of coal reserve in many parts of the globe. So, if we have to think of protecting our nature, but at the same time if we want to use this conventional fossil fuel for some more time before we are confident or before we are used to with the use of renewable energy resources and generation of hydrogen, this coal can be a good source of hydrogen production. So, but at the same time it is not helpful in for the environment. So, if we have to take care of this environment and hydrogen simultaneously, what we need to look at that we have to reduce the emission of this greenhouse gases, and not only that we have to we have to think about enhancing the overall efficiency of this process. So, is there any chance that we can rectify the use of use of coal, or is there any process which can be helpful in utilizing this coal in a better way? So, that is what we are now trying to look into. Here at this point we will be talking about integrated gasification combined cycle or IGCC. Okay. So, what does this process means? It is basically a kind of clean coal technology, unlike that where this conventional coal usual pulverized coal or powder coal is directly burned and it was generating the steam. Basically this coal is fired and then finally the steam is produced, and that steam will be used to generate or run the turbine to generate the power. That is what is the thermal power plant, that is how it works. But this process where integrated gasification combined cycle works, it is basically why do we call it as clean coal technology, because you will find that this gasification is integrated with this process. So, when we are trying to use this coal, we are trying to instead of burning it directly, like you have seen that the coal is burned to generate the steam in a steam engine. We are mostly familiar with the old fashioned steam engine, where the coal will be burning and that will generate steam and that will run the that engine, but those are obsolete these days. Okay. But if we look at this gasification part or the partial oxidation part, so where instead of directly burning the coal, what we are doing is that we are mixing it with the oxygen part, and we are trying to generate a syngas. So, here this syngas generation CO plus H2, and that will come at quite high temperature. So, that high temperature, as we have learned that this PO partial oxidation reaction. So, if we are taking this coal and then we are partially oxidizing it, that is basically what we are doing is the gasification we are trying to do, and that will generate not only the syngas, it will also generate a high temperature. So, that high temperature will basically that radiation zone, if you look at, and radiation zone followed by the convective zone, we can put our this water to generate the steam in that process, and at the same time we also have this syngas that can also be used for generating the power. So, here instead of directly burning the coal to generate the steam, we have generated the CO content of it plus H2 content of it, as well as we have created a high temperature, but of course, we need additionally this oxygen for this kind of integrated gasification combined cycle. So, this gasification or the partial oxidation will generate some CO plus H2, which can be again fired to generate another what is called the steam turbine. First of all, the steam will be used for generating the power, as well as this CO plus H2 can either generate this H2, we can take out this H2 and store it for a longer time, and otherwise this CO plus H2 will also be used as a fuel to generate the another steam turbine to produce the power. So, this is what is is needed. That means this cogeneration of this CO plus H2 and power and hydrogen is possible with this use of coal. So, this is a better effective way of utilizing the coal, and that is why it is called the clean coal energy technology. It is because another and there is another reason for that, I will just tell you in a short while. This overall efficiency is again improved from the earlier process, and here this greenhouse gas emission is a bit less compared to the other processes, because here we have the possibility of removing CO2 in bulk from the process, and of course, we have the generation, because we are using this oxygen, this generation of NOx is bit less in this process, and this elements like mercury and etcetera will be removed with the along with the slag that is being formed. So, the in a nutshell, this integrated gasification or IGCC process is bit advantageous over the conventional one, and these processes are in the newer generation of this thermal power plants since 1995 onwards, they are in use. So, this is about the generation of hydrogen using if anyone is interested about generating the hydrogen from coal, one can think about this particular process where gasification, we have talked about it while talking about the utilization of coal, and there this we have talked only about the partial condensation, but along with that this partial condensation, if we can try to bigger scale, if we look into it, we can generate the steam along with that and generate power if it is a big plant. Okay. So, now we will talk about what is called, as we have learned in the earlier processes where we are talking about this, I will go back to that, where we have talked about the raw gas or this raw hydrogen formation from the water gas heat reaction, or even steam reforming. After the steam reforming, we have or the partial oxidation also, we have talked about this this mixture where methane, CO and H2 would be there, and from there depending on the extent, this CH4, basically this natural gas component, that is the methane, if it is in large quantity or in small quantity, that will be determining the processes as we have talked earlier, in the earlier slides. So, that is basically I am sorry. So, we are talking about the cryogenic condensation part. This cryogenic condensation is when you have the less methane content. So, we have talked about the steam reforming, we have talked about the partial condensation, partial oxidation, and there we have seen that it is generating the CO plus H2. Along with that, it is not that all the every amount of the methane, for example, in the natural gas, and it is getting utilized. So, that means some amount of methane may come along with the product. So, depending on its quantity, we decide whether we should go for this cryogenic condensation or we should go for methane scrubbing. So, this is a typical cryogenic condensation. This picture has been taken from this industrial gas processing edited by H.W. Herring 2007, but it looks a bit complicated, but we will just look into the salient features of this kind of processes. This is basically a cryogenic process where you will find that it is harnessing the difference in the boiling point of hydrogen and all other components. Okay. So, the hydrogen normal boiling point H2 is 20.3 Kelvin roughly, and then we have the CO, and then we have the what is called CH4. This methane normal boiling point is 111.7, and this is 81.65 Kelvin. So, these are the normal boiling points of these components. So, if we look at this this 20.3 K is quite low from this 81.65 or methane at 111.7. So, here let us look into this basically the different components here. There are plate fin heat exchangers, then we have 1 and 2 are this component 1 and component 2 are basically the bridged aluminum plate fin heat exchangers. These two are the heat exchangers, multi-stream heat exchangers. Then we have the separator. This component 3 is basically a separator, and component 4 is the hydrogen stripper, whereas this 5 is COCH4 separator, or separation column. So, these are basically typical chemical industry equipments, but of course, these heat exchangers are quite common in our thermal engineering applications. So, here what we see is that we have the raw synthesis gas. That means, we have a mixture of CO plus CH4 plus H2, and that is coming and getting cooled in this heat exchanger number 1 and number 2, and they are cooled to such an extent that when it comes over here, this will be cooled down, and it will separate from H2. H2 will be coming out. So, this is what is that raw hydrogen we have talked about so far. This raw hydrogen will be coming out, whereas this other part, that is COCH4 mixture, will stay back. This COCH4 is again we cannot throw it out just like that. So, here in this hydrogen stripper, whatever remaining part of the hydrogen which is there in the COCH4 mixture will be taken out from this column, and that will come out as fuel gas. So, that means this is basically the H2 which we could not recover completely, and we could not put it in the raw hydrogen. So, that part will be coming from this hydrogen stripper, and that will come as flue gas, and we will burn it to I mean in the steam reforming reaction. If you remember that we have said that it needs some fuel to burn, and that fuel was coming partly from the PSA tail gas, as well as sometime we have this fuel gas coming from this kind of separation processes. So, here then this a part is getting separated. So, we have on this side is CO plus CH4 mixture, and on this side we have separated the hydrogen. These are the typical columns, and here this COCH4 mixture will be coming over here, and again this will be separated into CO and CH4. So, as we understand that CO plus CH4, if we have mixture, then CO boiling point is 81.65 as we have understood, and this is having 111.7. So, this is lower boiling point, this is the higher boiling point component. The higher boiling point component will be at the bottom of the column, as we have learned earlier, and the lower boiling point component will be on the top. So, from here we will have the CO part, and this CO will be going back as a product. Okay. But there is something component 6, that is basically the compressor part. Here we will find that this initially we told that this raw synthesis gas is getting cooled. So, who is providing that cooling? It is basically this this compressed CO part will be expanded, I mean compressed part will be expanded, and then it will be cooled down, and while it is getting evaporated, that provides the refrigeration to the incoming high pressure this synthesis gas. So, as a result, what we find is that this is basically the CO product, but it is also providing the refrigeration, necessary refrigeration for the condensation of this the raw synthesis gas. But as we have also learned that this is meant for low methane content, when the reaction is such that this CH4 slippage is a bit less, and that is in those cases we can go for this cryogenic condensation. But if it is such, this is the boiling point of the normal boiling point of CO, that is 81.65, already we have written it. Okay. So, now let us go back to our discussion on the other part, where we have talked about that the methane scrubbing will be necessary, where we have slightly higher methane content in the raw synthesis gas. That means, this raw synthesis gas, where it is basically the CO plus H2 along with methane. But if methane is less in quantity, we can go for condensation as we have shown earlier, but if the methane content is slightly higher, we should go for a methane scrubbing part. Again, this diagram has been taken from the industrial gas processing, and one can look into this book for other part that we have talked about. So, now let us look into the different components we have. We have the heat exchanger, then followed by 1 and 2 are the heat exchangers. Again, these are plate fin heat exchangers. This is PF plate fin heat exchanger. So, this would be PFHX, and then we have this 3 is the scrubbing column, CH4 scrubbing column, 4 is hydrogen stripper, and 5 is basically the COCH4 separator. So, here the point is that again we have earlier we were we were in the other process we have seen that we were condensing the gas, and condensation was by condensation we were trying to separate the hydrogen from the rest of the component, but here what we are trying to do is that we will use CH4 liquid and subcooled CH4, where this all other component like COCH4 part will be scrubbed, or it will be dissolved in it. So, here what we need is a supply of cold subcooled methane from here, and that will dissolve the COCH4 part, and remaining the hydrogen part will be coming from here as raw hydrogen. So, this raw hydrogen is basically produced here by scrubbing the COCH4 using the COCH4 part will be scrubbed with the help of this CH4 part, okay, or the liquid methane will be necessary. So, that is generated here. You can just try to follow it, but first of all this raw hydrogen is coming out, and at the bottom of it what we have is the CO plus CH4 mixture. Along with that, some amount of hydrogen may be there. So, we have the hydrogen what is called stripper. So, this will from the top of it you will have what is called the hydrogen part would be there, a small bit of it, and that will will come as flue gas. You can see that this is what is giving you the flue gas, but at the bottom of it you have the CO and CH4 mixture. So, this COCH4 mixture will now come to this separation column, where the bottom product would be the methane liquid, and on the top part you will have the CO. So, this CO will go back again as a CO product, and here in addition to this compressor you can find that there are expanders. So, this expander will also generate some amount of cooling, and here what we have is the liquid methane. So, this liquid methane is coming to this methane pump, and finally, that will be taken inside, and what we have all these cold components will be placed inside a cold box. While talking about the cryogenic processes or liquefaction, this will be dealt in details. So, that is about this cryogenic separation processes, which are basically integral part of any hydrogen production unit, where be it say steam reforming or partial oxidation or autothermal reformer. So, reforming process, you will have this syngas, and syngas from the syngas processing is done either with this methane scrubbing and by condensation process. These are of course some of the cryogenic processes. There are other process by which probably the CO2 will be removed and etc. So, that is about these separation processes, or the syngas processing. So, these are the references you should refer to. Many of this discussion has been made from this industrial gases processing, and then you can also read this book on cryogenic hydrogen technology, and In conclusion, we can say that we have learned about the processing part, and I mean where we have talked about the syngas processing, and we have also talked about the better utilization of this coal, where this coal gasification can be added with the thermal power generation process, and that will enhance the that will enhance the efficiency of the thermal power plants. So, this is about this hydrogen production part. In the next lecture, we will try to talk about the coke oven gas, and from there how do we produce hydrogen. Thank you for your attention.